Signal processing underpins advancement in fields like telecommunication and medical imaging. One persistent challenge is spectral leakage, where signal energy spreads to adjacent frequencies, distorting analysis. Windowing function, such as Hamming and Hunt windows, address this by tapering signal edges in the time domain, reducing discontinuities and improving frequency domain accuracy. Each window presents a unique balance between frequency resolution and side lobe suppressions, making application-specific selection crucial. This project focuses on the design of a Hunt window and its performance in comparison to the Hamming window through analysis using MATLAB. By studying their respective effects on composite signals, we highlight how windowing actually reduces spectral leakage. The findings have practical implications across several fields. For example, in audio engineering, they can enhance sound quality, while in telecommunication, they can improve signal clarity. And last but not least, in the biomedical application, these insights boost diagnosis accuracy. Overall, this advancement paved the way for further research and innovation in signal processing.
My name is Yusrina Ida Anibintiazi. My metric number is B122310302. I'm going to demonstrate the use of Hunt window to analyze signal in both frequency and time domain. First, we define some basic parameters. Here Fs is our sampling frequency, which is 1000 Hz. N is the number of samples, 256, and frequency specific the two frequencies that our signal will contain. Next, this creates a signal composed of two sine waves at 50 Hz and 55 Hz. The time vector t ensures proper sampling according to the defined frequency. Next, we define and apply the window to the signal. The Hunt window is a type of tapering function that reduces spectral leakage in frequency analysis. Applying this window smooths the signal at the boundaries. After applying the windows, we compute the FFT, which is fast Fourier transform, FFN here. The FFT gives us the frequency spectrum of the signal, and we normalize the result for better visualization. Finally, we plot the result. The first subplot shows the frequency spectrum. This plot highlights how the Hunt window supervises side lobes in the frequency domain, showing the main lobe clearly around 50 Hz and 55 Hz. The second subplot shows the time domain signal after applying the Hunt window. This illustrates how the signal is tapered in the time domain, reducing the absurd discontinuities at the edge. And this is it. This code effectively demonstrates how to use a Hunt window for spectral analysis, highlighting its benefit in reducing spectral leakage. So here's the result. In the top of subplot, we see the frequency spectrum of Hunt window signal. The x-axis represents frequency in Hz, while the y-axis shows the magnitude in decibel dB. Notice the two distant peaks at 50 and 50 Hz, 55 Hz corresponding to the frequency in our original signal. The Hunt window has effectively reduced the side lobes, ensuring that the energy is more concentrated in the main lobe. This makes it easier to distinguish the two frequencies. The plot also demonstrates how the Hunt window improves spectral resolution by reducing spectral leakage, a common issue with a raw FFT analysis. Moving to the bottom subplot, we see the signal in the time domain after applying the Hunt window. The x-axis represents time in seconds and y-axis represents the amplitude of the signal. Notice how the signal tapers smoothly to the zero at the both ends. This effect of the Hunt window which minimizes discontinuities and reduces the absurd transition in the signal. This smooth tapering helps to mitigate artifact in the frequency domain, which is why the Hunt window is commonly used in signal processing. Overall, this result demonstrates the utility of the Hunt window in both the frequency and the time domain. It enhances the clarity of spectral analysis by suppressing side lobe and reducing ringing effect in the time domain. This makes it as a valuable tool for analyzing signals with overlapping or closely spaced frequency. Thank you.
My name is Nazar Zelina, and I will explain about the Hamming window. So this coding is to demonstrate on how the Hamming window is applied to a signal. So this Fs is sampling frequency, which is 1000 Hz, and the N is for the samples number, which is 256, and we are combining the two frequency, which is 50 and 55 Hz, into one signal to simulate, and then we are going to analyze the frequency. And then next we are using the Hamming window command to create the Hamming window, and the Hamming window signal to apply the window by element wise multiplication. Then next we are using the plot to plot the graph result. So I will run the coding, and this is the signal loop in the frequency domain after applying the Hamming window. So the big central peak is called the main lobe, which is represent the main frequency component of the signal, and the smaller bump on the side are called side lobes, and the Hamming window making the unwanted frequency much smaller, and the Hamming window makes the signal mean frequency stand out more clearly. And then the bottom one is the signal after applying the Hamming window in the time domain. So the edge of the signal are smoothed out, which means the signal taps on 0 at the beginning and at the end. So in the time domain, it is a smooth signal which helps the frequency analysis clean and accurate. So that's all from me. I will pass to the next person.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Kaikal bin Kamaluddin. Matrix number B1223105883. Okay. Now we first look at the parameters. Look at the parameters that were given. The sampling frequency is 1000. The number of samples is 256, sorry. And the frequency was set at 50 to and 55 Hertz. Okay, then times 0 and minus 1 divide frequency sampling to generate our signal. Okay, sin 2 times pi frequency times time sine 2 pi 2 times pi times frequency 2 times time. Okay, next to generate our Hamming window, define window Hamming equals to Hamming n. Next, Hamming window signal times Hamming window to compute FFT, frequency Fourier transform. Okay, for the frequency axis. Next, the frequency shift, and for the normalized frequency. Next, Han window. Define our Han window. Han window equals to Han n. To apply Han window into the signal, Han window underscore signals time Han window. To compute Han window signal to filter Fourier transform. This is for frequency axis. Frequency shift to generate frequency in the window and later. And then Han FFT makes Han FFT for normalized frequency. Next for the plotting, I can rewind. Okay, based on what we got here, Hamming window doesn't to a narrow towards the edge of the zero, right? Because but sorry, but it creates a slightly higher edge amplitude. This design is reduce the height of the first side lobe more than the Han window. Okay, the Hamming filter graph shows a slightly sharper drop off a drop off in the frequency, because when you look at here at the middle, it cut the negative, it cut off the drop off frequency. But its ripple side, but in the ripple side, are a bit stronger further than a little bit stronger than the hand windows frequency, hand windows filters. Okay, the amplitude at the edge, the hand windows tapers mostly towards zero at the edge. All right, providing a better side lobe suppression and minimizing the noise leakage. The trade-off between the two windows lies in their priorities. The hand windows favor side lobe suppression over the frequency resolution. Meanwhile, the humming windows prioritize better frequency resolution, but in exchange of increased side lobe level. The hand windows filter, yeah, hand windows is commonly used when in speech or in audio processing application, where its superior side lobe suppression makes it ideal to minimize the huge frequency. It is also to utilize in communication systems such as FDM to suppress the distortion leakage, as well as in radar or sonar system to reduce the side lobe interference. Meanwhile, in humming window, in contrast of humming window is particularly used for application that demands a high frequency resolution, such as to identify the harmony or closed space tone in audio analysis. It is also applied to communication in communication system to resolve closely space tone in space frequency in component to modulated signal in radar or sonar system by detecting narrow signal in noisy environment. To narrow the signal in noisy environment. Okay, excuse me. It is ability to provide a fine spectral detail makes it suitable for the high resolution spectral analysis.
So for the conclusion, we can conclude that this study evaluates two window functions, which are the Hamming and the Han, using digital signal processing to showcase their characteristic of spectral leakage and resolution. For Hamming window, it is suitable for those applications which require minimal spectral leakage, including speech processing and noise reduction, where accurate frequency separation is not considered crucial. And for Han window, it is suitable for application requiring enhanced frequency resolution, such as in the analysis of music and narrowband signal processing, where the discrimination of closely spaced frequencies is imperative. For the recommendation future work, we can investigate alternative window function, which we can explore Blackman and Kaiser window for different trade-off, and we can adaptive windowing techniques to develop techniques to adapt window choice based on signal characteristic, and we can do real world application testing, which is test Hamming and Han windows with real signals like audio and biomedical data. And the last one is improve visualization tools that can create interactive tools to illustrate trade-off between key metrics. Addresses this area can extend the capabilities of windowing techniques for a wider range of digital signal processing application. So that's all from us. Thank you.